Okay, Kyujin, it's your turn. So your screen is now shared. So unmute yourself and hand it over to you.
All right, thank you very much, Fumiya, for organizing the nice workshop. So I think I have lots to show, so I'll go fast. Just like everyone, I think embodied intelligence to me was also a very important theme. And I think the first time, my memory is a little bit vague, but I'm not sure if it was or not, but I met Rolf Viper at the soft robotics workshop back in 2013, 14, around that year. And he actually, after I presented my work, he said the things that I'm working on is embodied intelligence. And then I had a chance to invite him to Korea back in 2016. And I had a chance to, better understand what embodied intelligence is, I think. And basically, as everyone knows, it's something like this. It's computation outsourcing to the body. And this is one of the examples I use to explain body intelligence compared to humanoids. Like this kind of hexapod doesn't have to think. It just, humanoids, you have to really control really well to overcome this kind of obstacle. But, if you have legged robot, you don't have to do that. And if you tune those stiffness very well, you can overcome these very well. And I remember, oops, sorry about that. I remember Rolf Viper explaining embodied intelligence using, by showing a single motor. And then if there's a single stick attached to a single motor, you create this motion. You have 2 sticks attached, you create more complicated motion. 3 sticks attached, you create that kind of like more complicated motion. And I think my understanding of embodied intelligence is a little bit narrow compared to other people. But I think since I'm a designer, I was more focused on that. And when I asked Rolf about, so it's really hard to understand, and what Rolf said was, if we see more and more examples of these embodied intelligence, then we'll be able to better define what embodied intelligence is. Since then, I think I've tried to, come up with many different examples. So my understanding is, right now, most robots, you have actuator, body separately designed. You design the body, you attach the actuator. I think with embodied intelligence, what you have to focus is on using simple actuation, but with combining it very intelligently with structure characteristics. Then you'll be able to create, reduce the cost of computation and control, and still get many interesting behaviors or interesting motions. And compared to these hard robots with, limited degrees of freedom, soft robot has so many infinite degrees of freedom. So you will have to do something to be able to control soft robot. So I know many people are trying to model this and those kind of efforts, but for me, so one of the things that I did initially when I came to Korea was deformable wheel using this kind of like so many numbers of SMA, 16 SMA actuators. And this is what introduced me to origami. So I think my viewpoint of origami is a little bit different from Jamie's, because this was my initial motivation for using origami. I wanted to simplify the actuation. And this is the wheel that we created. I think many people should know this video, so skip. And then we used this wheel for creating Snowmax. So we were able to make it a little bit bigger and still able to change the wheel. And then we worked with a tire company in Korea and made it to a real big size tire, which actually can hold up to a 1,000 kilograms. And actually, so we were able to put it on a wheel. So it has just very simple actuation, but it could create this kind of motion. And it could, we are using basically fabric to resist the load, and fabric is hard enough, I guess. And it became a commercial in Korea. So this was on air in Korean TV commercials for a while. I think it was around 2 years ago. And this is another example of like simple control, adaptive behavior done with Sam Fractal and Robert. It automatically changes the size of the wheel depending on the load. So if you have a heavy load, the wheel automatically changes so I think its intelligence is embedded into the structure. And another example, I think this is, our soft robot is a good example of embodied intelligence. You just put in air and you create these kind of behaviors. So we moved this further. We wanted to move this further by combining this soft robot motion with origami folding pattern. And we created, and one interesting point is that by just changing the stiffness of certain segments, you can create different motions. So which means that if you do variable stiffness, then you can create different motion. So just by changing the stiffness of certain body parts, you can change the motion. So we actually created what's called a origami durable fin stretchable origami. It's compact. One of the reasons that we did this was we wanted robot to start from very small size and then become a workable robot size. Actually, pelican eel has a similar behavior. So we also built a pelican eel, and also we created different examples of like crawling, gripping, and different things could be. And we created this one because if you see the big hero, actually they start from like very folded state and then it becomes a robot. So we did something similar. And this video, I've shown this since 10 years ago, fly trap. This really excited me because it uses bistability. And with a simple actuation, you can create a real quick motion. So, this is because of the bistability, and, artificial muscles is really hard to use. It's really hard to control. But if you use the structural characteristics, then, on-off state. So you can change from one state to the other. I think I got hooked into this bistability concept early on, and we made these kind of like grippers, and we actually also, this is what we call buckling gripper. This is also a very interesting example of embodied intelligence because when this flexure buckles, instead of a linear spring, it becomes a nonlinear spring. So even if you have multiple fingers, all those fingers are going to generate same force despite they are at a different angle, which creates a very stable grasping. So it's a simple simple control, so it reduces cost of calculating all those shapes and everything, and we can do a very adaptive grasping. And it's scalable, simple design, so you can make small, large, those kind of things. Also, we use this for creating a ladybird inspired origami structure, because this is what the ladybird beetle uses. It sort of has that kind of bistability in the joint, and it can open its wings really quickly. So we use it to create the glider wing, which can like open quickly. Why do you need to open your wing quickly? When you jump and glide, after jumping, you have very small time gap to open up. So if you use this kind of structure, then you can really quickly open up. And then you can attach different mechanisms because it's really lightweight. So you can do jump crawling. You can do jump gliding, crawling, and those kind of things. This is what's called a case crawler. Again, very simple structure, very flat. You can even make it into a phone case. So we call it case crawler. And, it was on YouTube and people were saying, what's this? Why do you need this kind of thing? But the sole purpose of this was to show that even with this simple structure, we can actually, it has a high payload. That was the point. And this one, again, this one is not published yet, but we are using the snail's tentacle structure to create a vacuum that changes diameter. Again, bistability. Instead of changing continuously, we have 3 steps. So you can change into different sizes. So very stable at that size. And so we actually combined our origami structure with the diameter changing vacuum gripper, so we can can pick up many different types of things. And again, our water strider also has that embodied intelligence because it's very simple, and it uses what's called torque reversal. Very simple actuation is just a SMA actuation, but because of the torque reversal, it's very simple, very lightweight, but it can do this kind of jumping on water. cannot do it with like complicated control. So, and then this is, okay, so I think I'm out of time. So this one, but let me just share with you like this, what's called a swimming leaf. So, you know, inside the water, the leaf, you know, when it falls, it flutters, right? So it creates this kind of fluttering motion. So our idea was to use buoyancy inside the water to create this kind of fluttering motion. And we created this kind of a fluttering motion. So it's sort of an inverse of the what they call the dropping leaf. So you can climb up. And we create this kind of swimming leaf, and we can actually control by segmenting the actuation side. We can actually control the direction. So you can also turn and do those kind of things. And the one example of application we tried to show was, you know, if there's an oil spill, maybe we can have this like folded and then open up, and then, you know, you can do this kind of things, and then it can be attached to a object and then pull it up, something like that. And our exoglove also has that kind of embodied intelligence because you know, we have a differential mechanism that is very simple, and we can actually be embedded it inside our glove, and without any like complicated control, you can grab many different objects. So again, like I said, I think my definition of embodied intelligence is very narrow, but I think it's because I'm more based on the design side, and simplicity is very important. And, you know, being able to create this kind of adaptive complex motion with just simple control is really fascinating for me, especially if we want to, you know, commercialize these kind of technologies. I think being simple is very important. So, for us to make sure that, you know, the things that we are doing impacts the society, I think we need to make this available to society, which means we have to commercialize it. So I think I'm not saying that it can be commercialized, but I think it increases the possibility. So thank you very much.
All right, thank you, Kyujin. This is a wonderful presentation, and I like especially all this fast forward of incredible robots that you built so far.
Sorry about that.
No, this is really helpful overview.
I couldn't figure out what to take out, so I just.
Yeah, thank you.
It's related to me in my viewpoint. So.